Hello, everyone. My name is Nanxiang Zhao. You can call me Sam. I'm a PhD student from DCMB, Dr. Alan Boy's lab, and our lab focus on genomics, especially about like regulatory elements like enhancer and promoters. And in today's talk, I'll talk about one tool that we recently developed called FC2. So FC2 is a P color that we recently developed and is improved based on the original version Dr. Alan Boyle developed back in 2008. And we improved that with dynamic statistics. And now this tool has been published in the NAR Genomics and Bioinformatics. And if you're interested, you can go ahead and check out this paper. But for today's talk, we will have like mainly 4 sections. The introduction, a little bit background about the P calling, and also the methods used in the FC2, and also the second section is methods, which is a methodology, like methodology adopted in the FC2, and some results of FC2 to show why FC2 is a very good general P color, and it outperforms the very popular P color Max2 by a lot. And then at last, we will have a hands-on demo to show this how to use this P color as well. And so let's get started. So first of all, introduction, I will start with a statement like P calling is the most important analysis, a very core analysis in the high-throughput sequencing data analysis. And P calling is defined as the computation methods to identify areas in genome that have enriched rates compared to a background in HTS experiment. And the accuracy of P calling results is very important for any downstream analysis like peak differential analysis, footprint analysis, and motif enrichment analysis. So this is one of the reasons why we want to improve on our previous version, and also that's why we think why the P calling field was keep moving forward. And today we're going to talk about P calling. So speaking of P calling, most P caller usually start with reconstructing the genomic signal. And but different P callers employ different ways to construct a signal, but most of them fall into 2 categories. The first one is to extend the reads to the mean fragment length. And this way you get some interval sorts of the fragments. So for example, as you can see here, so first of all, we map the reads to the genome, then we extend to the mean fragment length. Then in this case, we will get the interval sorts of the signal. But one disadvantage of this strategy, as you can see, the signal always like non-smooth, and it really depends on the fragment length that you estimated. So another approach is to treat those as a point source. So what I mean by that is like you shift those rays like by half of the mean fragment length and now extend those, and then you get some point source of the cut rays. And this is one common way to deal with those rays is to using a moving histogram. And but the histogram is actually very problematic because it's strongly affected by the choice of the bins and starting locations. For example, you can see here, those 2 data points are identically distributed. But if we choose a different starting location, you generate very different histogram profile. So this is a very big problem for the histograms. And so what should we do? So KDE came to rescue. So KDE stands for kernel density estimation, which is a non-parametric estimator. So the essential idea is like instead of like binning those data points into certain bins, we will model each race with a kernel. For example, here we model each race with a Gaussian kernel. Then we add up those rays. We generate a smooth and very accurate and also very interpretable signal, which is that the signal is the probability of finding certain rays at a given base pair location. And this is very good, like it's applied in many areas, and it's very accurate and proved to be good for the P calling as well. So to formally define the KDE, so KDE defined as the sum of the kernels some of the Gaussian kernels and normalized by the number of arrays. And especially in the FC2, we use a unnormalized version, which is we don't normalize by the number of arrays, but just a little bit detail to formally define this. So let me see. So so with the KDE being a better estimator, we developed the first p-color ever with the KDE back in 2008, which is called FSeq. So FSeq used KDE to intuitively summarize the sequence data, and we also developed a simulated background to allow very accurate identification of the biological meaningful sets. And FSeq have been widely used in the ENCODE project and other project for the DSeq data and FAIR-seq data. And it's shown to be the most accurate and sensitive p-color for the DSeq data. However, there are some shortcomings of the original version. The first one is being like this p-color is developed like back in 2008. So it's like 13 years ago. And also there's some inherent shortcomings of this p-colors, With being said, like there's no support for user input control data, which really limit the ability to estimate the background distribution of those rays. And this becomes a big problem for when we p-calling for chip-seq data, because always chip-seq data will come with a control data set, but won't be a big problem for attack-seq or the DSeq data. And also there's no test statistically reported, and which limits the ability to account for those local biases, which I will explain in a minute what I mean by this local biases. And the third one is which is inherent from the above two. There's no consideration of the local biases. So in order to improve and update our p-color, we developed FSeq2. So FSeq2 is a complete rewrite of the original version in Python, and we developed this new statistical framework so that we implement dynamic parameter to conduct local statistical analysis with underlying percent distribution. And by combining the power of the KDE and this local test, we found out it can robustly account for the local biases and solve tests when ranking those summits and peaks, and making the result very suitable for the IDR analysis, which I will talk about in a minute as well. And also we bring many new features to the p-color to make it compatible with other p-colors now. So here is the GitHub page of the FSeq2. So next up, we're gonna talk about the methodology employed in the FSeq2. So first of all, let's talk about the workflow. So this is the workflow of the original FSeq. Sorry, wait. Can you hear me?
Yes.
Oh, seems like there's something wrong with my, I can't move my mouse. Let me see. Give me 1 sec. I'm really sorry about that. I don't know what happened, but I can't move my screen. Sorry about that. So let's. So are you guys seeing the presenter view or the?
It looks good.
Okay. Sorry about that. I was there's some technical issue there. And so where are we? So here is the original workflow of the FC, and here is start with a treatment data, and then we will estimate some parameters for this treatment data, and then we will shift raise if it's a chip-seq data, and then we will calculate a KDE signal, which is kernel density estimation signal of those treatment data. Then we will call candidate summates relative to background. So this step is different from the original FC. Original FC focused on the peak regions, but now we focus on the candidate summates to test for those summates to get more accurate and better results. So what have we developed so far? First of all, we add a control for, we add a support for the control data, and we will do the same for the control data set. And then we take both KDE signal to calculate a p-value with a dynamic parameter. After that, we will calculate the q-value use Benjamin-Hochberg FDR rate, and also then we filter the summates. And in the end, we will optionally output 3 files: the signal, the big wig signal, the significant summates, and also those broad peaks. Broad peaks contain at least one of the significant summates. And also, if you have replicate, we can do this doing this for another replicate, for example, replicate 2, and we'll concatenate those two to a concatenated version, and then we also run peak calling on those files, and we will run into an IDR framework to better identify those significant peaks. And I will talk about this framework in a minute. And you will end up with a plot to see, okay, where the significant cutoff will be reasonable for your data set, and also the IDR threshold peaks. So, and the most important part of the methodology of the FC2, which being this, we developed this new framework for the calculated p-value. And let's talk about this part in a little bit detail. So first of all, what is a dynamic parameter? So instead of like fitting into a single underlying distribution, we want to calculate a background distribution for each sum is going to be tested. And this distribution will vary along the genome. But you probably wonder why you want to calculate a dynamic parameter. This is because we observe the reads correlate very well between the treatment and the control. So as you can see here, like this is a Fox A1 chip-seq data, and the x-axis is the treatment reads, and for 10 KB window, and the y-axis is the control data set. You can see a relative well correlation between the two. And this suggests a redistribution with some local fluctuation and biases. If using one fixed underlying distribution, then we will result many false positives because like there's some local biases need to be considered. And those are being some, for example, local chromatin structures, the amplification, sequence biases, and so much more. We need to consider them locally. So this is the dynamic testing idea. However, if you're familiar with the p-calling algorithm, you will know this idea is not completely new. This is idea originally developed by Max2, and we adopted and modified this idea from it. And we test through a lot of settings, and we found out the local person is a very effective underlying distribution to use, and when it's very fit to our settings. And the specific settings is being like, for example, if we see the number of reads enriching a region follow a Poisson distribution and characterized by lambda local. And we define the lambda local as the following: the maximum of the following different aspects of the lambda, and we take some maximum of it. And in this case, we can better remove the false positive due to the local biases, because like those different lambdas are zooming on different regions of the local regions to get a better idea of the local environment. So just to repeat myself, the highlight of FC is like we develop a statistical framework that combines the power of KDE and also the statistical testing, the local testing. And KDE can capture the surrounding information better, and the dynamic testing idea can convert this into interpretable p-value. So one thing probably to notice is that like Person is a discrete distribution, while KDE generates some very continuous signal, like with some floating point. So how we actually bridge the KDE with this dynamic idea? So we use linear interpolation of the p-value in log space. As I said before, like for example, number of rays follow the Poisson distribution. We calculate the p-value by the survival function of the Poisson distribution like this. And then we have this, we define this y as a continuous variable, and we just do a linear interpolation in the log space to have to have a continuous p-value actually, and so that we will allow those rays to be continuous variable and linear interpolation of those p-value. You probably wonder why we want to doing this linear interpolation in log space, because we observe the survival function of the Poisson distribution for in log space is linearly approximate with the x, with the number of rays, and we think this is a good enough approximation for our usage. And so just repeat myself, we transform this discrete Poisson distribution into the continuous Poisson distribution, but this is not like mathematically proved the counterpart of the continuous Poisson distribution. But it's good enough for us to bridge the KDE with the dynamic testing idea and solve more tests when we ranking those submits. Okay, so this is the most significant part change of our algorithm. And after talking about this, I will show you a list of new features which has been brought into the second version. So first of all, this is a complete rewrite in Python, and we take advantage of very well optimized Python libraries and like KDE and PyPy2s. And this is very easy to refactor. This is like due to Python. So during development, we have testing so many ideas to see which one works best for the KDE. And yeah, and also it's very easy to import in the Python environment, also easy to maintenance later as well. And also we add multi-processing support and also p-value, q-value calculation, as I said before. And also we have better quality control on the summits being called, and more improvements like pair and raise, flexibility of the IO bound, allow control data, and so much more. And among all those improvements, I would like to point out two new important features I will talk about. The first one is the fragment filter based on the fragment on the length information. The second one is the integrated idea analysis. So first of all, let's talk about number 8. So one thing we come across a lot during p-calling is like we want to improve the accuracy of p-calling by filter out the not relevant rays, and this is also very true for the ataxic dataset, because like ataxic assay both the open chromatin regions and also some nucleosome regions, right? And this is like, but oftentimes we only want to call peaks on those open chromatin regions. So what should we do? So in the original paper, the author said like the ataxic fragment length will indicate where those fragments are. For example, if the fragments like length under 100 base pair, they are most likely from the nucleosome-free regions, which is open chromatin regions. If it's between 180 and 247, then most likely from the mononucleosome regions. And in a renal paper, what the authors do, they only include those 100, less than 100 base pair fragments for the open chromatin analysis. However, for us, we design an auto filter for the open chromatin peak calling by filter out only nucleosome related fragments. So the difference is like we not only include those under 100 base pair, we also include those between those regions, between those ranges. For example, between 100 and 180. And I will show you a detailed plot later, like when we see the results of FC2 to see how we exactly do that. So we keep more fragments because we found out this is actually better for us to model the background distribution. And then also we filter out multi-nucleosome rays, which represent the condensed heterochromosome, and that won't add much information to the background estimation. So this is an auto filter we designed for ataxic data. And also you can design your own filter by plotting, for example, this plot. If you see, okay, the range, I think is not like 180, you can shift a little bit and directly input the our command line tools. So that would be a good thing to do. And so this is for the ataxic fragment filter. And the other thing is I want to talk about is of the new feature of the FC2 is the integrated IDR analysis. So IDR stands for irreproducible discovery rate. So basically the idea is like we want to use the replicate information to better identify the significance cutoff for those peaks. And the intuition is like if the replicate is measuring the same biological events, then the general signal will have like very high self-consistency. But the noise, like false positive, they seems to be more random ranked. For example, I will explain here. So for example, you can see here, the x-axis is the peak rank of, for example, replicate 1. And the y-axis is the peak rank for the replicate 2. If we if a smaller value means a higher rank, then the higher, if these two replicates measuring the same biological thing, then the higher rank peak will have a very good correspondence between each other. It's more like a linear. So this is a fake example. This is perfect correspondence, but in real case, there will be a more linear relationship between the replicates. And after some decay, at some point, they will translate to the noise peaks, which are not like significant peaks. Then those noise peaks will have this no correspondence between each other. And the algorithm of the IDR is to reliably to identify this decay point. So you probably wonder, okay, why we want to integrate this IDR analysis? Because in our practice, we found it is a very reliable way to identify the significance cutoff. We found out like actually most of peak callers, including us, when we define the threshold for the peak for the significant peaks, they are often like heuristic based and kind of arbitrary. And especially when you compare the results of different peak color, you see okay, those significant scores are in different scales or in different format as well. However, IDR uses relative ranks instead of absolute values, and they also integrate this replicate information to better identify this significance cutoff. And it's very effective in the TF chip-seq data analysis because it's already part of the encode data analysis pipeline. So, and this is why we want to integrate this in our tools as well. And I will have a demo of the IDR analysis at the end of the talk. So, so although this IDR analysis is very compatible with different scales, signal scales and types, it indeed favors a certain output for the accurate identification of the decay point, which being like you have to have the ability to call an extensive list of peaks, like 300K number of peaks. And this actually becomes some problem for some peak color, for example, max2, because when you lower the threshold, they call broader peaks instead of like they can reproduce the original peaks that they set for lower threshold. And also you have to have the separate score for individual summits, and that will work better because like you use the rank information and less test between summits. And by design, FC2 is very suitable and compatible with IDR analysis due to the following reasons. We design like this and to make it very workable with the IDR as well. And the good news is that this IDR is already integrated in our pipeline and with our tuned settings. So you can directly use the IDR analysis if you have a good quality replicates to do so. So next up, we're gonna talk about the results of the FC2, which is basically to show like why FC2 is a better generic P color and how it outperforms max2, which is a very popular P color. So we'll be focusing on the chip-seq taxi because we have been shown perform very well on DNSeq and FairSeq. And we'll benchmark with 4 other P colors frequently used by the Inco project: max2, SPP, music, and jam. And we will benchmark on 100 simulated chip-seq datasets, 3 real chip-seq dataset, and 1 taxi dataset. And here's a plot showing the FC being the most accurate and sensitive P color for the DNSeq dataset. So let's first get into simulation testing. So for the simulated chip-seq testing benchmarking, we will evaluate with the F-score. So F-score is the harmonic mean between the precision and recall. And it's basically translated to like, for example, a higher F-score, which means a more balanced performance of the P color. And we will vary we will generate this operating characteristic curve by vary along the top ranked peaks, like especially specifically top log n number of peaks. And the shaded area is like the 95% of confidence interval of those 100 simulated data set. So as you can see, FC2 and the max2, they outperform other P colors. This actually suggests like the dynamic testing idea is very effective in removing the false positives, which are also consistent with another benchmarking paper showing that like this dynamic testing idea is very good for chip-seq data. And those 2 P colors are only 2 P colors implemented with this dynamic testing idea. And also we can evaluate this from another perspective. We can also evaluate how well the number of peaks caught by each P color using their default threshold and correlated with the number of peaks in the ground truth. And here is a box plot showing that. And as you can see, FC2 best correlated with the ground truth in terms of number of peaks caught by the default threshold. Those numbers are the correlation coefficient. And at this point, you may say, okay, the FC2 and max2, they perform similarly, very similarly. So what's the point of developing this? So FC2 really shines when there's no control data. And this is very surprising. Like when we, without control data for those chip-seq data set, we can achieve comparable performance when there's a control data set. And they outperform other P color by a lot, by a gap. And this actually suggests that the control information can be extracted from the treatment information because we only use the treatment data here, but this should be given certain conditions. First of all, we need a very statistical rigorous modeling methods, which in this case is our KDE. And also we need to develop a statistical framework to coherent with this modeling methods, which is our new statistical framework. And in this case, we can summarize those values into better representation of the p-values, and we can outperform other p-colors a lot by designing like this. And also, there's one more thing I need to mention is like in order to have this performance, the control data set and treatment data set, they have to correlate very well in large window sets. And which I have shown you, like in the previous slide, like actually for a good quality set of treatment and control, that should be always the case. And that will reassure the performance of the FC2 without control data could be very good as well. So, and also you probably wonder, okay, Sam, the chip-seq often comes with a control data set. Yeah, it often comes with a control data set, but how it applies to other assays when there's missing control? For example, ATAC-seq or DIN-seq, they are often missing control because the control data set is very expensive to generate. So in order to answer that question, we did a direct comparison with Max2, first of all, because it's very popular and reliable, and second of all, is the P-color, the ENCODE project used for the ATAC-seq data analysis. And we compare with Max2 and with different P-color mode. So for Max2, we use the single and shift and extend pair and mode, and use FC2 pair and auto mode and single and FC2 single and mode and more. And here also the original version of the FC. And one thing I want to point out is like the single and shift extend mode and pair and auto mode, they are Max2 and FC2 different strategy to avoid peak calling on those nucleosome regions. Their strategy to make the peak caller to focus on the open chromatin peak calling. And as you can see, the FC2 pair and auto mode and the MX2 single and shift and extend mode, they outperform other peak callers at a lower genome coverage. This is actually indicate using those strategies to avoid cause and nucleosomes can achieve higher precision for the top ranked peaks. Because x-axis is a top ranked peaks and in the scale of the genome coverage. And especially for like peak calling tasks for the in identifying open chromatin regions. And to be more specific, the pair and auto filter, what we include in this filter is, so here is showing a plot of that. So in the original paper of the ATAC-seq, the authors only include those fragments and the 100 base pair. But for FC2, we included those in between those nucleosome ranges as well, because those fragments actually give us a boost to of the performance due to we can better model the background distribution. And that's also why we observe this FC2 pair and auto mode to outperform the single and shift and extend mode by a lot. And also another thing you may observe from this plot is like at a larger genome coverage, the FC2 two other modes outperform others, and they peak at a different genome coverage. And this suggests actually FC2 can take advantage of the additional data points to improve the precision for, like, for example, medium rank peaks by more accurately estimating background distribution, because those two modes have more risk to model the background distribution compared to the FC2 pair and auto mode. And this is and you probably wonder, okay, Sam, what's the usage of this? What's the point of this? So I think the take-home message for this plot is like, so the more rigorous selection of those arrays, the more rigorous you filter on those arrays, then the more precision you will gain for those very top ranked peaks. For example, for the FC2 pair and auto mode. However, that also comes with the potential cost of filtering out some true positive as well. Like you can observe from here, like when you filter out some arrays at a higher genome coverage, you will end up with lower performance here. So in practice, if you care a lot about the top ranked peaks, then go ahead with the pair and auto filter mode, and otherwise you can choose single and or pair and without filter mode. So next up, we also wonder the superior performance seen in the simulated chip-seq dataset also can be reproduced in the real chip-seq dataset. So we benchmark on 3 more real chip-seq datasets. And the results is showing here. The difference is like now we are not using simulated dataset. That means we don't have a ground truth. And one common alternative to evaluate this is to use the fraction within like 100 base pair of certain TF motif. And as you can see, the FC2 has the largest fraction of the top and peaks within this base pair of the CTCF motif. And seeing the result from another perspective, which we evaluate from the empirical CDF, we'll see actually the gem stood out. Like 80% of the peaks of top 1,000 peaks, it's only within 4 base pair of a CTCF motif, and compared to MAX2 and FC2 around 30 base pair actually. And this is actually due to the GEM's additional ability to call peaks near those motifs. However, this may not be an advantage in most cases, which I will show you just in a minute. And also we will also observe similar trends in another real chip-seq data set, like the MAFK chip-seq data set. However, in another data set, like STAT1 chip-seq data set, all those peak colors had very low performance, and you really cannot like distinguish from each other as well. And this is actually indicate this motif distance analysis may not reflect the actual performance, because like Hoffman showed, like 76 out of 20 quantitative factors like relevant motifs in their chip-seq peaks, and the STAT1 were very low in the motif occupancy. That means if you call peaks near those motifs, that may not be a good indicator of the real data set. And here's a plot showing that like STAT1 is very low in the peak with a sequence motif. However, it's not one of the lowest one, and CTCF being the top one. So, and that concludes the results section. Then we will have a hands-on demo of the FC2. So here's a GitHub of the FC2, and we'll go through some installation tips and some basic usage and some hands-on example of p-calling on a taxi data and the chip-seq data work with the IDR framework. And here's some data set I generated from the ENCODE project, and but only include one chromosome due to the time concern. So I will start a new share screen to show that. In 1 sec. Okay, let's see. Okay, so here's the you guys can see my GitHub page, right?
Yes, we can see it.
Okay, cool. So here's the GitHub page of the FC2, and we go through a little bit. Here's some documentation of the FC2, and here we go through some details of the installation here. So we will highly the prerequisite is FC2 only work with Python 3.6 version and higher, and also you have to install the BitTools as well. And we highly recommend to prepare a Conda environment for the FC2, and then you can install from PyPy or Conda. And here is like I will directly activate the environment I have previously activated. So also you can install from the cells as well, and some integration test if you installed it, let's see if it works. And then we go back. So the main usage of FC2 includes three sub-command. The first of all is a copy, which is a main function to copy from those treatment and control data. And also copy IDR. So copy is followed by the IDR framework with the recommend settings. And also we have this wrapper for the IDR package. And here I will run those pieces. I will run this and run this. Oh, sorry, too much technical difficulties today. I think my sorry, give me one sec. Actually, I have tested, but I don't know what happened. I'm really sorry about this. Yeah, just my SSD is not working. I will start the share. Okay, actually, I will just go through this. There's some technical difficulties. So for the here on the GitHub page, there's some detailed documentation of the FC2, and yeah, you can read it through if you want to know more about those and output formats as well. And then we will talk about examples of the ataxic peak calling here. So you can call the copy command and with a treatment file, and here's a specific setting for the ataxic data, and then you can include this pair and auto filter here by including this command. And also you can render for chip-seq data and for the IDR pipeline, and you can call FC2 call IDR, and you supply with 2 replicates, and you can give a control files, and then some settings for the chip-seq data, and you can specify the multiprocessing as well. Yeah, this is for that, and I actually plan to show you the real results here, but it seems like my my SSD is not working now. I don't know why, but I will go ahead. I will skip that, and back to the. Okay, so but I will just briefly talk about the results of the IDR. So here is the IDR plot when we run those command we'll get. And if you get a very high quality of the replicate, you will observe something like this. So a linear relationship at the head and very random at the tail. And also if you have a very poor quality data, you have this more random case here. And yeah, this is to just show that about the IDR pipeline results. And just a little bit summary, like FC2, we solved the shortcomings in the first version, and we combine the power of KDE and dynamic testing. This really helps for account for local biases and self-test when ranking those summaries. It's very useful for this IDR analysis. And we can notice the high performance of cross-assays not only in the DNC, and also in the chip-seq and attack-seq. And also the results is very suitable to IDR analysis and also already integrated into FC2. And thank you, and I'll take any questions. Sorry about the technical issue. I tested it out yesterday, but there's some issues here.
Does anyone have any questions? So Sam, it does look like there's a question that was put into the chat box. I apologize for my barking dog at the moment, but in the chat box it says, "Great talk. Thank you for sharing this tool. Are there edge cases where FC2 and/or Max specifically struggle that can only be solved with experimental design?"
I would say yes. Like I would say like Max 2 and FC2, they both perform poorly when the read the sequencing depth is low. So I think that's if you observe the reads is like for example below 1 million, then that's especially for chip-seq data, and that would be a problem for both p-color and yeah, that would be that could be only solved by experimental design. So.
Great, thank you. Is entered in the chat box. Does anyone else have questions? You can either put them in the chat box or unmute yourself and ask if you have any. All right, well, I'm not seeing it. Oh, Brian, do you have a question?
Well, it's not a question, but I really enjoyed the talk. I came in a little late, but I really appreciate you coming, Nanxiang. Thanks so much. It was interesting. What I saw was interesting. And Chris, did you have any questions? I see you there. It's good to see you. Let's see. I just thought it was good.
Thank
So
you.
I wanted to register that. And I'm sorry I came in late. We just got off the exec committee.
Yeah.
So thank you.
Thank you.
Yeah.
Yeah.
Great. Well, I'm not seeing any other questions. So I want to thank everyone for joining us today. Hopefully everyone can join us again next week. We'll have GCal talking to us about building a software pipeline for developing and evaluating time series machine learning models using electronic health record data. So I hope to see everyone next week. And thank you again, Sam, for today's excellent presentation. So thanks, everyone.
Thank you. Thank you, everyone.
Thank you. Thanks, Marcy.